Brian Lenardo is joining us from Stanford University, where he is a postdoctoral researcher in the physics department. He obtained his PhD from the University of California, Davis. His graduate work, carried out as a Lawrence graduate scholar at the Lawrence Livermore National Laboratory, focused on characterizing the nuclear recoil response of liquid xenon detectors, with applications in the detection of dark matter and coherent neutrino nucleus scattering. Since joining Stanford, he has focused primarily on the Nexo Experiment, a planned next generation search for neutrinoless double beta decay that will be the subject of today's talk. Brian has received a number of fellowships, has served as a scientific consultant for film, and has been interviewed on public radio. In a topic which would be an interesting colloquium in itself if we invite him a second time, he regularly teaches college courses in astronomy and mathematics to students at San Quentin State Prison. Welcome, Brian.
Thank you very much. So let me just share my screen and I will go here. Yeah, thanks very much. I'm really excited to have the opportunity to talk to you folks today. The topic that I'll discuss is the Nexo Experiment, which is the next generation search for neutrinoless double beta decay, and I'll explain what that means. I want to start just because since we're remote with some photos of the last time I was in the area, just to, I guess, show you that I love northern New Mexico and been there many times. And I'm really excited now to have the opportunity to connect with the physics community at UNM. So thanks very much for the invitation. So the outline of my talk is shown here. I'll start with discussing why we search for this process called neutrinoless double beta decay and what it can tell us about the universe. Then I'll discuss the next generation of experiments which will search for this process in approximately 1 ton of material. Then I'll discuss in some detail the Nexo experiment, which is the experiment that I work on as a postdoc at Stanford. And then if there's time, which there may or may not be, I'll talk about how we would do the next generation experiment and go even deeper and study the mysteries of neutrinos. So we'll start here. And so the beginning of the story that I want to tell you today starts with the standard model of particle physics. So what you see over here on the left, you can think of as the particle physicist's periodic table. And so these are sort of the known fundamental constituents of nature. And what we call the standard model is the theory that stitches all of these pieces together and describes how these particles interact with each other. And what's amazing about the standard model is it's really one of our most precise and powerful physical theories. And my favorite example is you can calculate the magnetic moment of the electron and then measure it, and you can confirm the predictions of the standard model to better than 1 part in 10 to the 12, which is just an astonishing level of precision and really makes this one of our greatest achievements in fundamental physics. However, the standard model, while it's very precise, does not account for all the features of nature that we know of. And one of these big mysteries is that when we look out at the universe, we see that it's full of galaxies and stars and plasmas and all this stuff, but we don't see any antimatter. And this is a really interesting mystery, right? Because you see lots of galaxies, but you don't see any anti-galaxies. And the implications here are that in the very early universe, when the universe was in thermal equilibrium, it was a hot bath of particles and radiation mixing in thermal equilibrium, somewhere in that soup of hot particles and radiation, there was an asymmetry created that created more matter than antimatter. And then that asymmetry, as the universe evolved, sort of condensed into the matter that we see in the universe today. So that asymmetry was very small. It was only about 1 part in 10 to the 10, but it must be there to explain the abundance of matter and the lack of antimatter that we see out in the universe today. And what's really mysterious about this is we actually can't explain this within the standard model of particle physics. So we've studied in great detail many of the different interactions between the particles you see over here on the right, and we've not yet been able to find one that can explain this imbalance between matter and antimatter in the early universe. So this remains one of our biggest mysteries in both particle physics and cosmology. And so we need to look a little bit deeper. And in fact, we have some hints from the neutrinos. And so that's the focus of the research that I do. So neutrinos are the most abundant particles in the universe. They're the uncharged cousins to the charged leptons, which are the electron, the muon, and the tau particle. They have three flavors, which are assigned to each one of the charged leptons. And they're interesting because they interact only via the weak force. So they're extremely weakly interacting. And in the standard model, they were originally assumed to be massless particles. So they're just these neutral massless particles that interact weakly through the weak nuclear force. But it turns out that they actually don't quite fit into the standard model as we know it. And the reason we know this is because of a phenomenon called neutrino oscillations. So neutrino oscillations are is a name that we give to the fact that if you prepare a beam of neutrinos of a certain flavor, here's an experiment called the Dune Experiment, which is an example of this. You prepare a beam of neutrinos, say as muon neutrinos, and you let those neutrinos propagate across some distance to a detector, then by the time they reach the detector, that beam of muon neutrinos is now a mixture of different neutrino flavors. So it's illustrated here on the bottom, where if you start at distance 0 with a beam completely composed of muon neutrinos, then as it propagates, if you measured it at different distances, you would see a very characteristic change in the mixture of different neutrino flavor states. And in fact, that mixing happens with a very well-defined and well understood periodicity. And the implication here is that the neutrino flavor states must be non-simultaneous eigenstates of this some mixing matrix that mixes with mass states of the neutrinos. And so this is, sort of a quantum mechanics problem where you have three states that are not simultaneous eigenstates of three other states. And so as they propagate, there's some mixing over time according to the Hamiltonian of the system. But what this really means, sort of at its core, is that there are three distinct eigenstates of neutrino mass. And that means neutrinos cannot be massless particles, as we had previously assumed. And so the discovery of this phenomenon was really a huge deal, and continues to be a huge deal, and resulted in the 2015 Nobel Prize in Physics, awarded to Art McDonald and Takaaki Kajita. So we know neutrinos are massive, but we've never measured the mass of neutrinos. And so despite our best attempts, we cannot observe a non-zero mass of the neutrino because they're just so small. So over here on the left, I show a picture of the Catron experiment. This is an enormous spectrometer that does extremely precise measurements of radioactive beta decay of tritium in an attempt to measure the neutrino mass kinematically. And the best result that they've come up with just about a month ago is still consistent with 0. And so you can use this result to put an upper limit on the mass of neutrinos of about 0.8 eV per c squared. So we have this understanding of neutrinos where we know that there are three different mass states. We call that M3, M2, and M1. Neutrino oscillation experiments give us a very clear picture of the splittings between these mass states. So the sort of delta, what we call delta M squared, between the differences between them. But what we don't know is, first of all, what the absolute scale is. So if we have the lightest state, how far is that from 0? We've never measured the absolute mass of the neutrinos, so we don't know that. And we also don't know what we call the hierarchy, which is the ordering of these mass states. So we have two possibilities, the normal and the inverted. And so the two unknowns in neutrino physics right now are the hierarchy of the mass states and the absolute scale of these masses. But if we put this into perspective, what we do know about the neutrinos is that compared to the other particles, they're extremely light. So this is a plot of the mass on the x-axis of all the particles in the standard model, all the fermions in the standard model. You see over here on the right, the quarks, which are the down, strange, bottom, up, charm, and top, the leptons. And what you notice is that all of the charged particles in the standard model are sort of clustered in the sort of MeV to GeV range in terms of their mass. And our best upper limits on the neutrinos are way down at the other end of this scale. And this is a 6-order magnitude difference in the masses between the neutrinos and all the other known particles, all the other known fermions. Now, of course, we know that the masses of the charged fermions are generated via the Higgs mechanism. And this is extremely well established and measured very carefully. But this huge 6th order of magnitude difference raises a question of how we generate the masses of neutrinos. Because if we were to generate the masses of neutrinos via the Higgs mechanism, we would need to tune their coupling to the Higgs boson by about 1 part in 10 to the 12, which would be a very, very fine tuning of a fundamental parameter. And so this kind of gives us a clue that maybe there's something else going on in the case of neutrinos. So one of the most straightforward ways to solve this problem is by introducing what we call a Majorana mass for neutrinos. So what that looks like mathematically is you have the Lagrangian of the standard model. Neutrino masses have a term where they couple to the Higgs boson, but you can add additional terms that we call the Majorana mass terms that give additional parameters in the way that you calculate the mass of neutrinos that can be tuned to produce very light neutrino masses with still very natural couplings to the Higgs boson. And I won't go into the math here, but if you assume a very sort of natural value for the mass that you get from the Higgs mechanism, these additional parameters essentially allow you to tune this to reproduce the very light neutrino masses that we observe or that we have set limits on in experiments. What makes Majorana neutrinos so exciting is that this would have really profound consequences for our understanding of matter. So Majorana neutrinos would be really a fundamentally new kind of elementary particle because first of all, those terms that I showed you in that Lagrangian require an equivalence between neutrinos and antineutrinos. And this would be unlike any particles that we know about today. And then second, of course, these extra terms would generate a mass for fundamental particles without the Higgs mechanism. So again, this is something unlike anything that we know of currently. And then in addition, adding these extra terms in the standard model Lagrangian allows additional sources of violation of certain symmetries, specifically charge parity symmetry. And then in addition, those terms break what we call lepton number conservation. And these things taken together are really, would fundamentally change how we understand particle physics because it would provide possible mechanisms for building a matter-dominated universe. And in addition, the understanding, especially of violation of lepton number conservation, could really illuminate a path towards a deeper fundamental theory of nature. So I do want to spend some time discussing lepton number conservation because this is an important point, both from a theoretical and also from an experimental point of view. So lepton number is just a quantum number in particle physics, which is just that the number of leptons in the initial state of an interaction should equal the number of leptons in the final state of an interaction. That's what we call lepton number conservation. And the diagram that I show over here on the right is an example of nuclear beta decay. So you have a nucleus where one of the neutrons in that nucleus decays to a proton, and it emits an electron and an antineutrino in the final state. And so you start in the initial state with no leptons, and in the final state, you have a lepton and an anti-lepton. Those things cancel out, and so lepton number is conserved. If you have Majorana neutrinos, because you're establishing an equivalence between neutrinos and antineutrinos, the physics of this inherently violates lepton number. And what's exciting as an experimentalist is that now to search for Majorana neutrinos, we have a very clear experimental observable. We can go and perform an experiment that has some number of leptons in the initial state and look for a change in the final state. And then as a theorist, this is important because lepton number violation would provide information on the deeper symmetry structure of whatever theory is beyond the standard model. And the best experimental tool that we have as an experimentalist myself is something called double beta decay. So double beta decay is a process by which a nucleus undergoes essentially two beta decays simultaneously. So you have two neutrons converted into two protons in the final state, and then that emits two electrons and two antineutrinos. This process is totally allowed within the standard model, and as you can see, because we get two electrons and two antineutrinos in the final state, this conserves lepton number. And in fact, this is while it's a second order process, and so the half-lives of this decay are extremely long, it's actually been observed in 14 different isotopes so far. And the way that you look for this experimentally is by measuring the energy deposited of the outgoing electrons in some detector. So over here is a picture of what you might measure in an experiment, where the x-axis is the measured energy in units of the Q value, which is just the energy difference between the two nuclei in this reaction. And since the neutrinos carry away some momentum, the energy given to the electrons comes out as in a broad spectrum with an endpoint right at the Q value of the reaction. Now there's a hypothetical version of this process that we call neutrinoless double beta decay. And this is a very similar process, except that in this hypothetical version, the two neutrinos that would be emitted in the final state actually co-annihilate within the nucleus. And so you get only 2 electrons out. And you can see immediately that this does not conserve lepton number, because you start with 0 leptons in the initial state, and now you have 2 in the final state, and no anti-leptons to cancel them out. So immediately see that this is not allowed within the standard model. And if we were to measure this process, we would immediately demonstrate the Majorana nature of neutrinos and discover new physics. So what we look for in an experiment, because there's no neutrinos to carry away momentum, is we look for all of the energy in this transition given to the electrons. And so in the previous case, we had a broad spectrum. In this case, now we have a monoenergetic signal exactly at the Q value of the reaction. So many experiments to date have searched for this process by looking for this peak. None have found it, and the current best limits are set at half-lives of 10 to the 26 years, which is about 10 to the 16 times the age of the universe. So if we were to go out and build an experiment to try and measure this, we need to be able to translate the results into some statement about beyond the standard model physics. And the way that we do that is with an expression that I show here. So the half-life that you would actually measure, this is the number that comes from your experiment, is the neutrinoless double beta decay half-life. So you either measure this or put a limit on it. And then on the right-hand side of this equation, you have some parameter, which we call f, that quantifies the beyond the standard model physics that you're searching for. And then 2 additional coefficients that represent the phase space of the decay and what we call the nuclear matrix element, which is just the matrix element for the nucleus transitioning during the double beta decay process. And as it turns out, these 2 things, the phase space you can calculate, the nuclear matrix element is more difficult to calculate, but in principle comes from known physics. And so you can immediately translate a measurement of the half-life into some new physics parameter. And the baseline model that we usually assume is what we call light Majorana neutrino exchange, where if you draw a Feynman diagram, you essentially have 2 neutrons converting into 2 protons and 2 electrons coming out in the final state, and a light neutrino propagator mediating this interaction here. In this case, the new physics parameter f takes the form of an effective mass of that neutrino propagator that we call m beta beta. And this mass is just a certain linear combination of the neutrino mass states. So now we can take a measurement of the half-life and convert it into a statement about this new physics parameter m beta beta. So the strongest current limit, actually this is not the strongest current limit, this is the second strongest current limit now, I'm slightly out of date. But one of the best limits comes from the Dune Experiment, setting a half-life limit that must be greater than 1.8 times 10 to the 26 years. And that shows up on a plot that you see over here on the right as a constraint on this m beta beta parameter on the y-axis. Usually we'll plot this as a function of the still unknown absolute mass scale of the neutrinos, here represented by the sum of those 3 mass states. The 2 bands that you see here are the allowed regions of this parameter space under our different assumptions for the ordering of those mass states. So if the neutrinos are inverted, they show the allowed parameter space is bounded by the blue. If the neutrinos are normal, the allowed parameter space is bounded by the red. And so the best current experimental limits are coming in from the top and constraining Majorana neutrino masses down to about 100 millielectron volts. Before I move on, I want to talk about how the next sort of 10 to 20 years are really going to be a transformational era in neutrino physics. Because we're really going to narrow down our understanding of the allowed regions of parameter space in this plot. So the first thing is that the next generation of precision cosmology measurements, actually, because you can measure the impact of relativistic degrees of freedom in the early universe, will have sensitivity enough to measure the absolute scale of the neutrino mass. So next generation of cosmology experiments are going to come in and make a measurement along the x-axis of this plot, which is really exciting. The second thing is that the next generation of neutrino oscillation experiments, for instance, the Dune experiment that I showed earlier, is going to help us decide whether we live in the world of the inverted hierarchy or the normal hierarchy. And then finally, what we're going to talk about today is the next generation of neutrinoless double beta decay searches, which is going to push another order of magnitude down in this plot. And so really over the next 10 to 15 years, we're going to make dramatic improvements in our understanding of neutrino physics and have real potential for making some exciting discoveries on a variety of different fronts. So now I want to talk a little bit about how we search for neutrinoless double beta decay in the next generation of experiments. So before we get into that, I just want to tell you where we are currently. And basically the story is that there's a variety of different experiments that have either are currently operating or have recently finished operating, searching for this process in a variety of different isotopes. The common thing is that all of these experiments have sort of on the order of 10 to 100 kilograms of these isotopes and have set limits on the order of about 10 to the 26 years. To push an order of magnitude down, we need to improve our sensitivity to the half-life by 2 orders of magnitude. So the next generation of experiments aiming for that target will need to increase the amount of isotope that they're looking at, and correspondingly will have to lower their backgrounds. So how do we actually optimize one of these experiments? Again, we're looking for this peak here, which is at the endpoint of this broad spectrum of 2 neutrino double beta decay. And of course, these events are extremely rare. We've set limits on half-lives up to 10 to the 26 years, which gives you some idea of how infrequent these decays would actually be in an experiment. And so we're completely swamped by backgrounds, which come primarily from trace radioactivity that's just naturally occurring in the environment. And so of course, radioactive backgrounds aren't typically flat like this, but this is just a cartoon to sort of illustrate how we think about how to optimize one of these experiments. So the first thing that you do to optimize an experiment is you just assemble a lot of the isotope that can undergo double beta decay. And that just drives the signal rate up to a point where you might actually be able to see something on the lifetime of a normal experiment. The second thing is that you need extremely low backgrounds. And so this is done by, first of all, taking your experiment and burying it deep underground to shield you from cosmic rays that can induce radioactive backgrounds. And then also being extremely careful about what materials you use to build the detectors, because any sort of contamination in those materials can contribute radioactivity and create events that give you a background in your experiment. The third thing is good energy resolution. This makes maybe more sense if I flip back and forth. So achieving good energy resolution, because the signal is monoenergetic, sort of concentrates your signal into a smaller region of your data space and improves your signal to noise. And importantly, it allows you to separate that signal from the tail of this 2 neutrino double beta decay spectrum. And then finally, once you've achieved all of these things, you ideally want to be able to lower your backgrounds even further. And this comes from building a detector that enables you to do signal and background discrimination using the data. And so typically the way that this works is that most of your backgrounds are coming from gamma rays that are emitted by this environmental radioactivity. Gamma rays in the energy ranges that we care about tend to Compton scatter, leaving multiple energy deposits in your detector, whereas double beta decays in most experiments are highly localized point-like interactions. So separating interactions that have what we call multi-site versus single site enables you to lower your backgrounds even further. So the next generation of experiments that are trying to do this at what we call the ton scale comprises 3 experiments, basically, that are going forward with some component in the US. So the first is Nexo. This is the experiment that I work on. It will be a single-phase liquid xenon time projection chamber. I'll talk more about that in a minute. So I'll move on. The central one is what we call Cupid. This is an experiment that we used scintillating lithium molybdenate crystals. The isotope that they're looking to study is molybdenum 100. And this has several advantages. First of all, it's very cost effective. And then molybdenum 100, the double beta decay signal that they're searching for is above most of the backgrounds. It's a high energy transition. So they can do some very good science and mitigate a lot of their backgrounds just by being higher in energy. And then finally, there's the Legend experiment, which is an experiment that uses enriched high purity germanium detectors. With this technology, they've been able to achieve best-in-class energy resolution and do essentially background-free searches for neutrinoless double beta decay. So this is a very powerful technology using these crystals. And all three of these experiments are extremely competitive with one another. So just historically, I'll tell you about the progress towards the next generation. So this was identified in October 2015 by the Nuclear Science Advisory Committee as one of the top priorities in nuclear and particle physics. And so since then, it's been sort of a slow march towards actually getting something built. In November 2018, the US, the DOE issued what we call CD0, which officially formally identifies that they intend to fund large-scale experiments to do this science. And then things started really heating up over the summer, where in July, this past July, we had a portfolio review with the Office of Nuclear Physics, where the three experiments that I just described were invited to present their case and basically walk through their design and present their readiness. There was an additional workshop shortly afterwards where the Americans and Europeans held a sort of joint brainstorming session on how we could pursue this science more globally. And then over the last just couple of months, we've really started some forward motion where in January 2022, so just a couple of months ago, Nexo got formally started as a DOE project and will hopefully start construction in the very near term. And in general, I think it's really promising, this field, because the Office of Nuclear Physics has really identified this as a priority and formally declared that they're going to fund all three of these experiments going forward. So this is a slide that I showed from Tim Hallman, who's the Associate Director of the DOE Office of Science and Nuclear Physics, showing the comparison between the three experiments in terms of their sensitivity to the effective Majorana neutrino mass. You can see that they're all basically in the same range. And the DOE is currently working with international funding agencies trying to figure out how to support all three of these going forward. So now I want to talk a little bit more about the Nexo experiment specifically, which is the experiment that I work on. So Nexo is a global collaboration of people working on this science. The center of mass is really in North America with a lot of American and Canadian institutions, but we have a growing component of the collaboration in Europe, in China and Korea, and now we have recent collaborators from the University of Western Cape in South Africa. And we're pursuing neutrinoless double beta decay by looking at the isotope xenon-136 using a detector called a single-phase liquid xenon time projection chamber. So here I show the sort of cartoon of the experiment with the time projection chamber, which is the sort of heart, the main detector here in the center. It's essentially an empty volume filled with liquid xenon with charge sensing tiles, which I'll explain, and then light sensing tiles around the barrel. And then this is embedded in a cryostat to keep it cold and keep the xenon liquefied. And then all of that is surrounded by a giant water tank, which both serves as a passive shield from environmental radioactivity in the surrounding laboratory space, and also as an active veto for cosmic rays. All of this is going to be built deep underground at the Cno Lab facility in Sudbury, Ontario, where we have 2,000 meters of rock above us to shield us from cosmic radiation. So here's a picture of what that would actually look like. So Cno Lab is here. It's about 4 hours north of Toronto in Sudbury. We would operate in what we call the cryo pit, which is deep underground space, about 2 kilometers underground. And so we have a big cavern in which we would build this large water tank and then build a liquid xenon time projection chamber in the middle of it. So the reason we want to use a detector the liquid xenon TPCs as a detector technique is that they really are optimized for this type of search. So the way the detector works is you have a tub full of liquid xenon. And for every interaction that deposits energy in the liquid xenon, you get two measurements. First is scintillation light, which is emitted from that point of interaction very quickly and can be detected by photosensors lining the barrel of the experiment. And the second signal is the ionized charge, which you can drift under an applied electric field up to a collection plane at the top of the experiment. And so the dual channel measurement gives you really powerful three-dimensional imaging of each one of these interactions, because you get the XY position of the interaction from the drifted charge by pixelating the charge collection plane. And then you get the Z dimension by measuring the time difference between the arrival of the photon signal and the charge signal. And then very importantly for our purposes, because the detection medium is liquid xenon, and the isotope that we care about is xenon-136, we can enrich that liquid xenon in this isotope and have a very high efficiency search where the detector medium is also the sample that we want to study. So these detectors are really well suited for neutrinoless double beta decay searches for a variety of reasons. First of all, you can get a lot of your double beta decay isotope in one place because we can, as I just mentioned, we can enrich the target. And then these detectors are highly scalable. So there's already operating liquid xenon TPCs with the order of 10 tons of xenon in the middle. Second is that these types of detectors are very low in background, and they have very well characterized backgrounds in the MeV range. And that's because the xenon itself can be made extremely low in radioactivity. And then also xenon, when it's liquefied, is actually quite dense. So radiation that would come in from the outside and create backgrounds in the detector is highly attenuated in the outer regions of the detector. So you get this self-shielding effect where the innermost region of this experiment is extremely low in background and very sensitive to search for very rare decays. The third thing is that we can get very good energy resolution by combining the light and the charge signals. And then finally, because of the three-dimensional imaging capability of this detector, you get very good signal and background discrimination because you can tell the difference between a gamma ray, which deposits energy in multiple places, versus a double beta decay event, which is highly localized. So we take all of this information that we get from the TPC and turn it into 3 dimensions in which we can do our analysis to search for neutrinoless double beta decay. On the left-hand side, the first dimension that we use is the energy, and this is just simply reconstructed as the sum of the light signal that we detect and the charge signal that we detect. And the reason for that is that the light and the charge signals in liquid xenon are anti-correlated. And that's because the ionization can recombine and create scintillation light. So you get this interesting anti-correlation in which if you try to measure the energy of an interaction with either one of these signals alone, your energy resolution is quite poor. But if you take the sum, you effectively rotate your energy measurement in this 2-dimensional space and can get very good resolution. So the plot that I'm showing here is a simulated background spectrum with a monoenergetic signal at 2.6 MeV. So you can see if you're looking at it on the diagonal, your resolution on that peak is quite good. The second analysis technique that we use is, of course, the 3-dimensional event topology, which allows us to do this separation between the multi-site and the single-site interactions. This, of course, lends itself to image recognition, and so this is a place where we plan to use machine learning. Our simulations are now analyzed using a deep neural network discriminator that gives us very good discrimination between backgrounds and signal. And then the third dimension that we use in our analysis is what we call the standoff distance. And this is where we take advantage of the fact that liquid xenon shields the backgrounds coming in from the outside and keeps the center of the detector extremely low in background. So the standoff distance is just defined as the distance from the TPC's outer edge. And you can see that gamma ray backgrounds fall off very steeply as a function of this parameter, whereas neutrinoless double beta decays, because they're coming from the xenon target material itself, are distributed uniformly and fall off much more gradually. So in order to understand how sensitive Nexo will be, we need to be able to predict the backgrounds very carefully. And we've done a huge amount of work in doing this in a very data-driven and robust way. So we can break the backgrounds expected in Nexo down into essentially three categories. The first is from radon-222, which is a noble gas and can mix into the xenon and create backgrounds that way. The second is what we call intrinsic radioactivity, and this is from trace amounts of uranium and thorium and other radioisotopes that are just found contaminating any of the materials that we use to build the experiment. And then the third, which is a far subdominant component of our background, is what we call exposure-based. And this is where we account for things like cosmogenic activation, from cosmic ray muons that make it down to the deep underground laboratory, and then solar neutrinos. And I want to impress upon you the level of detail with which we model our projected backgrounds. What I'm showing here is a breakout of our intrinsic radioactive our backgrounds from intrinsic radioactivity as a function of each of the components in the detector. And you can see that the level of detail here goes all the way down to things like the epoxy that we want to use to assemble the charge readout, or the solder that we want to use to assemble the light readout. And each one of these points comes from a real measurement where we've taken the material that we want to use and measured its contamination using extremely sensitive radioassay techniques. And so this allows us to build a very robust and powerful projection of what backgrounds we can expect when we actually assemble the Nexo experiment. So we can take that background model and run it through our Monte Carlo and give us the actual distributions that we expect in our data as a function of the three analysis dimensions that I mentioned before. So on the left, again, you see the energy. In the middle, you have the deep neural network, which is just the machine learning single-site, multi-site discriminator. And on the right-hand side, you have the standoff distance, which again is just the event distance from the chamber wall. And the signal that we're looking for is shown by the shaded blue, and all of the different backgrounds are shown by the various color distributions. And what you see is, what you're looking at is all of our projected data projected onto each one of these axes individually. And so the point here is that if we were to just look at the energy or to just look at the standoff, our search for this blue spectrum would be hopeless because we'd be totally swamped by many orders of magnitude of backgrounds. The power of Nexo is being able to combine all three of these dimensions into a simultaneous three-dimensional analysis. And so we can cut in that three-dimensional space in what we call the region of interest, which is a region that's close to the energy that we care about. It's a region where most of the events are single site, and it's a region where we're looking at only the innermost volume of the detector. And so if we make a selection in that three-dimensional space, we can actually see that by combining these three pieces of information, we can actually discover this extremely rare process. So what I'm showing here is the same sort of three-dimensional distributions where the backgrounds have a slightly different combination, but the signal that we're looking for is still the shaded blue spectrum. The black points represent a simulated data set that we could actually expect to see after running Nexo for about 10 years. And the data set that I'm showing is assuming a half-life of 0.74 times 10 to the 28 years. And if this were the data that we actually got in Nexo, we can statistically calculate that we would discover Neutrinoless double beta decay with a significance of 3 sigma. So because we haven't built the experiment yet, we can run a lot of these Monte Carlo experiments and calculate our expectation for how sensitive Nexo would be if we were to run it 1,000,000 times and take the median. And so that median, the median of the many different Monte Carlo experiments is how we report our sensitivity. And that's what I'm showing here on this plot. So the left, the y-axis is the half-life of Neutrinoless double beta decay in years. And the x-axis is the lifetime, which is just how long we actually run the experiment. For reference, I show the sensitivity of the XO200 experiment, which is one of the current generation experiments that also uses the liquid xenon TPC technology. And you can see that basically as soon as we turn Nexo on, we're going to blow past that by over and over magnitude. And then after 10 years of operation, our sensitivity has improved on current experiments by over 2 orders of magnitude. In terms of the physics for each of these experiments, we can now translate that sensitivity into a sensitivity to the effective neutrino mass, this M beta beta parameter. And we see that we push an order of magnitude deeper in sensitivity to new physics covering a lot of the allowed parameter space under the normal hierarchy, covering essentially all of the allowed parameter space under the inverted hierarchy, and really dramatically improving our potential to discover Majorana neutrinos. So in the last 10 minutes or so, I want to talk a little bit about something that I think a lot about in my free time, which is okay, we're going to build this highly sensitive, incredibly low background, and incredibly specialized experiment called Nexo. Can we do other science with it? Can we do stuff in addition to having world-leading sensitivity to neutrinoless double beta decay? And one of the things that we've been thinking about in the last couple of years is solar neutrinos. So of course, we know that the sun is a large fusion reactor. And if we look at the fusion processes that take place in its core, they can be broken down into two categories. The first is what we call the PP chain that starts with standard proton-proton fusion and proceeds through a chain of different reactions to fuse heavier and heavier elements. And then the second cycle by which energy is produced in the sun is what we call the Cno cycle. And this is a similar sort of proton-proton fusion process, except that it's catalyzed by the presence of heavier elements. So it's catalyzed by carbon and nitrogen and oxygen, which gives it its name. And if you look at the various products that are produced along each of these chains, you find a lot of different isotopes that are unstable and that decay, and in doing so, emit neutrinos. And so the sun is essentially constantly emitting this huge flux of neutrinos from a variety of different reactions. And if we can measure those neutrinos, because they're very weakly interacting, they transmit information about the fusion processes directly from the core of the sun all the way to Earth without any sort of interaction in the outer layers of the sun. So essentially, it's a picture of exactly what's going on in terms of nuclear reactions directly in the core of the sun. And so there's a rich predicted spectrum from all the various isotopes. And I show that over here. This is a plot of the flux of neutrinos as a function of neutrino energy. And each one of these different lines is a different component that comes from these two cycles. One of the sort of unsolved problems in solar astrophysics is what we call the metallicity problem. And that's that the measured solar abundances of heavy elements, where heavy elements are defined as elements that are heavier than helium, are actually in tension by about 4 sigma. So there's 2 different measurements you can do. One is spectroscopic measurements of this photosphere. The other is helioseismological measurements of how sound waves propagate through the sun. And they actually favor different values for the content of what we call metals. The challenge here is that the stellar evolution models assume homogeneity. And so if we have these conflicting measurements, that tells us that our models of how the sun evolves need some fine tuning and are currently incorrect. And why this is important is that the sun, of course, is our neighboring star. And it provides a calibration for how we understand the temperature and the age and the chemical composition of distant objects that we observe through our telescopes. And second, if there's really a non-uniform distribution of heavy elements in the sun, this can have implications for how the solar system formed and whether or not there was accretion at various stages of the evolution of the solar system. So we need to sort of try and understand this. And as a neutrino physicist, there's an exciting opportunity here, which is that neutrinos that come from the Cno cycle, because it's catalyzed by heavy elements, the flux of those neutrinos provides a direct measurement of the abundance of carbon, nitrogen, and oxygen in the sun's core. And specifically, the Cno neutrinos are the spectra that you see over here in green and blue. And so if we can measure these with high precision, we can actually potentially answer this fundamental question in solar astrophysics. So Cno neutrinos are notoriously difficult to detect with neutrino detectors. And actually, this has been noticed, and people have sought to do this for many, many years. And it wasn't until the summer of 2020 that the Cno experiment was finally able to make the first measurement of Cno neutrinos through sort of Herculean experimental efforts in reducing their backgrounds. So the Cno spectrum that they measure is over here on the right. What you see in the data is the combination of all kinds of different spectra from both neutrino components and also background components. And the measurement they're trying to make is they're trying to measure this red spectrum here on top of all these other backgrounds. And you can see that it's an extremely hard measurement to make. And in fact, while this is an incredible measurement that they've made, unfortunately, the uncertainties remain too large to provide a solution to this question about the solar metallicity. So what we've proposed is to try and do this with experiments like Nexo using a process called inverse beta decay in Xenon-136. And so this process is the process by which a neutrino absorbs on the nucleus and emits an electron, converting the nucleus into cesium. And it's basically the inverse of nuclear beta decay. And of course, in Nexo, we have a lot of Xenon-136, so potentially we could see solar neutrinos via this reaction. And the important thing is that the reaction threshold is low enough that you can actually see the Cno neutrinos potentially in the Nexo detector. Now, of course, we also have problems. While we are a very low background experiment, we're not totally background free. And so we would need to be able to identify these events unambiguously in order to actually make this measurement. And so what we propose to do is we propose to look for reactions where the neutrinos leave the nucleus in an excited state, and then that excited state emits gamma rays that are characteristic of cesium-136. And so we can tag the production of cesium in the final state and reduce our backgrounds. So modeling this process requires us to understand a little bit of nuclear physics. So Xenon-136 has a spin parity ground state of 0+. And because a neutrino tends to want to proceed through what we call gamma-Teller transitions, the neutrino interacting on the Xenon-136 nucleus will preferentially populate states that have spin parity of 1+ in the cesium nucleus. So what that looks like is the neutrino capture populates a very specific excited state in the nucleus, which then relaxes to the ground state through the emission of these gamma rays. The challenge here is that nuclear data in cesium-136 is actually very sparse. So here you see all the measured states through which that could relax. But if you actually do a nuclear physics calculation, the shell model calculations predict a much richer spectrum of states that makes it much harder to predict which gamma rays would be emitted, and so harder to predict what signature you would actually see in the Nexo detector. So we wrote a paper on this collaborating with some nuclear physicists to try and understand this a little bit better. So we use the shell model to predict the relaxation process down to the ground state in cesium-136 in order to build a signal model for an experiment like Nexo. And what we found is something very exciting, which is that the shell model predicts the existence of a low-lying state whose decay would be delayed by up to hundreds of microseconds. So essentially, you would populate this state, it would relax down to this low-lying state, and then hundreds of microseconds later, you get the emission of a delayed gamma ray. And the point here is that in a detector, what you would see is you would see some primary interaction, and then after some characteristic time, you would see a delayed emission of a gamma that could allow you to do a time coincidence analysis that would dramatically reduce your backgrounds. And according to our calculations, looking for this type of signature could reduce our backgrounds to much less than 1 count in an experiment like Nexo. So we could do a background-free search for solar neutrinos. What you get for free, which is also very exciting, is certain models of dark matter which predict a very similar signature in a xenon detector. So there's models of dark matter where your dark matter particle would absorb on a xenon nucleus and leave you with the same final state. And so if you can do this delayed coincidence tagging, where you look for this specific time signature, could enable Nexo to produce world-leading sensitivity to these models of dark matter particles. The problem, of course, is that all of this relies on our predictions of the nuclear structure of cesium-136. So we need to go into the lab and actually try and confirm this. And so over the last couple of years, I've been working on a program to do this measurement using what we call charge exchange reactions, which is sort of bread and butter nuclear physics. You use proton beam impinging on a xenon gas cell to create cesium-136 in the final state. That creates a neutron in the final state as well. And so you can use this sort of kinematics of this reaction, measure the energy of the outgoing neutron to tell which state you're populating in the daughter nucleus. And then you have an array of gamma ray detectors to measure the transitions and identify the transitions that occur as that excited cesium nucleus relaxes down to the ground state. And so this program is ongoing. Here's just a picture of our pilot experiment at the Triangle University's nuclear lab in Durham, North Carolina. What you see in the left is our target chamber, where we have this connected to an accelerator that provides 7 MeV protons. here's our target cell, and then the neutrons fly off to the right. Zooming out, you see the picture over here on the right where the target chamber is shown here, and then the neutrons have a 13-meter flight path to this array of neutron detectors that you see here. And that 13-meter flight path allows us to measure the time of flight of those neutrons and therefore calculate their energy. So the plot that you see here down on the right is our first result, which is that we can populate the low-lying states of interest. These are the energy levels that you see here in the cesium nucleus. So we can populate those states with this proton-neutron reaction. And now we're currently working on instrumenting this with gamma ray detectors to try and measure the excited states in the daughter nucleus. Since it's already 3:22, I had a last section where I talk about where we would go beyond Nexo if we need to go further. I think I'm just going to skip that and go directly to the summary, which is just that neutrinoless double beta decay is an extremely powerful way to search for new physics. The next generation of experiments, which include Nexo, are going to push 2 orders of magnitude further in our sensitivity to the half-life of this process. And in conjunction with things going on in cosmology and other places in particle physics, really make this an exciting time to be in neutrino physics. Nexo in particular is a robust and very highly optimized experiment with some very interesting capabilities. And I think and it has a lot of potential to do very interesting science, both in fundamental particle physics and potentially in astroparticle physics as well. And so with that, I think I'll stop there and take questions.
Thank you very much, Brian, for this very interesting presentation. And let me just ask the audience to speak up with their questions. I see that Doug Fields has his hand up. Doug, we can't understand it, Doug. I'm sorry.
There's something.
No, it's not working, Doug. The audio is not working. I'm sorry. Well, while Doug addresses that, are there any other questions?
Well, I'd like to make just a correction for the benefit of students who might have been misled. Neutrinos are probably or possibly the most numerous fermion, but not the most numerous elementary particle. There are more photons, more gravitons, and there may be more dark matter particles.
Yeah, thank you, Kevin.
Bye.
Any other questions or comments? Doug, if you'd like to type your question into the chat, maybe we could go from there. I see Pseudonym has a question.
Hi, yeah, I was wondering, does the double beta decay prove anything different than discovering the sterile neutrino?
Yes, I think it's a different. Yeah, so sterile neutrino searches are maybe if I go back to this slide here. So sterile neutrino searches are searching for additional generations of additional flavors of neutrinos that would mix with the known neutrino states. Searching for neutrinoless double beta decay isn't directly a search for additional generations of neutrinos. Rather, it's a search for, it's trying to understand the way that neutrinos obtain their mass and the sort of symmetries that they obey.
Is there any difference in identifying the neutrino as a Majorana particle?
No, so right. So searching for neutrinoless double beta decay is the way that we experimentally can determine whether neutrinos are Majorana or Dirac. So if we observe neutrinoless double beta decay, neutrinos must be Majorana particles.
Okay, gotcha. Thank you.
And that's exactly what we're trying to learn.
Can you hear me now?
Yes.
Sounds good.
Okay, sorry about that. Can you go ahead and go over your slides for what comes after 10 scale?
All right, sure. Yeah, okay. So the idea here, I'll try and do this very quickly, is that if you need to go deeper, you need to go bigger, because to have sensitivity to sort of another order of magnitude and sensitivity to the effective Majorana mass, you need to push another order of magnitude here. You need another 2 orders of magnitude increase in your sensitivity to the half-life. And if you just do some very simple algebra to get one event per year, one decay per year at that sort of scale of half-life, 10 to the 30 years, you would need to be looking at 300 tons of material. So you need to scale up your detectors, scale up your experiments by another 2 orders of magnitude. And it's not simply a problem of building larger detectors, but it's also a problem of lowering your backgrounds. And so this is actually a very interesting plot, which is the sensitivity to discovering the Neutrinos double beta decay half-life as a function of how much exposure you have. So this is your detector mass times the amount of time that you run it. And the point here is that each of these contours represents a different background level. And so all of the currently existing experiments, if you extrapolate them out at their current background levels, still will not reach the sensitivity to 10 to the 30 years. So you need some technology that scales up to larger scales, but also reduces the backgrounds. And just to say it very quickly, liquid xenon TPCs look really promising from this point of view, because naturally, as you scale them up, you get more self-shielding. And so you get additional backgrounds suppression just by virtue of having more xenon in the detector, just because gamma rays are less good at penetrating into the center. The big challenge is really, the big problem for xenon experiments is that it's hard to get xenon. It's both very expensive, and also there's just not a lot of it produced worldwide every year. And so the current R&D on this front is to scale up the next generation of experiments is actually going into how do you actually pull xenon out of the air to get more of it than is currently available on the market. And so we actually we wrote a paper on how to do this with a bunch of people in the community, sort of as part of the SNOMAS process, that says both, this may be actually, without some dramatic improvements in our technology, liquid xenon TPCs could potentially reach the next generation, and also there may be some paths forward to actually acquiring the xenon to do that.
Thank you. I mean, given the news out of Dune as far as the costing goes, which I don't think has anything to do with the argon, it's probably not a good idea to point to Dune as an example of a kiloton scale.
Yeah, that's fair. That's a fair point. But yeah, thanks.
Thank you. I think the next question was actually Dinesh's. Did you still have a question, Dinesh?
No, I was actually, Doug had asked me the question to ask. And
Oh, okay.
so
Okay.
fine.
So,
Thanks.
okay, thanks. We have a question from Tusif Reza.
Yeah, thank you, Brian. It's a very interesting talk. I was wondering, for normal beta decay process, our spectrum is just continuous spectrum, but when Neutrinoless double beta decay, will have no neutrino in the final state. So still our energy spectrum is continuous, or it should be like line spectrum? Because most of the energy is like carried out by your final state nucleus and the electron particles. So it should be the line spectrum.
Yeah, that's exactly right. So that's how you distinguish these two cases. So in double beta decay is a process that we've observed many times. It's a natural process and has exactly this broad spectrum, because as in single beta decay, you have neutrinos carrying away some of the momentum. And exactly as you said, in neutrinoless double beta decay, since you have no neutrinos in the final state, all of the energy, essentially all of the energy, is given to the two electrons. And so you have a monoenergetic signal. So the way to distinguish between these two cases is by looking for that monoenergetic signal instead of this broad spectrum.
Okay, thank you, Brian. Thank you.
Are there any more questions from the audience? If not, then speaking for the audience, thank you very much, Brian, for this interesting talk, and hope that we can invite you for face-to-face talk sometime in the future.
Yeah, thanks very much. I really appreciate the opportunity, and thanks everybody for your time.
Okay.
Very, very nice talk, Brian.
Thanks, Doug.
Thank
Bye-bye.
you. Bye-bye.
All right, bye, folks.